Today podcast, I want to spend some time on voltage drop testing. And this is one of them topics that I have taught for a long, long time. And I still think it is one of the most misunderstood things in entry-level electrical. And that is kind of saying something. Because by the time most students get to this point, they do know the meter, at least, the basic functions, volts, ohms, continuity, where the leads plug in, how to read a DC voltage number, all of that stuff is usually there. But then we ask them to actually use the meter, not just read it, and that is where things start to kind of come apart a little bit. Because now we are asking them to look at a number on a screen and translate that into what is physically happening in a loaded circuit. And that is not the same thing as just taking a battery voltage reading. That is a whole different level of understanding. And I have seen it for decades. Good students, hardworking students, paying attention. And still, when voltage drop comes up, you can tell they do not quite own it yet. They are hearing it, but they are not really hanging on to it. And I think part of the reason is, electricity is invisible. You cannot see it. You cannot watch it move through the wire. You cannot look at a connection and say, yep, that connection right there is costing me 300 millivolts or 800 millivolts under or 2.5 volts under load. You cannot do that. So the meter has to become your eyes. And that is really what this topic is about. Learning to trust the meter enough and then learning how to think about what it is telling you. Now, like a lot of instructors, I have used the water analogy over the years. Pressure, restriction, flow, gauges, all of that, and that is fine. There is nothing wrong with it. It is a good place to start. But I always felt there is kind of a bridge missing. In other words, the students can understand the water picture, but then when it is time to go to the vehicle and actually put the DMM on something, they are still not always sure how that analogy turns into a meter reading. That is where I started using what I call the money method. And honestly, that worked pretty darn good. What I would do is convert the electrical values into US dollars and cents. So a battery at rest, 12.6 volts, became $12.60. Charging voltage, 14.6 volts, that became $14.60. And then if I had a drop of 0.2 of a volt, that became 20 cents. If I had 0.6 of a volt, that became 60 cents. So just to keep that really clear, because that decimal point matters, 20 cents is 200 millivolts, 60 cents is 600 millivolts, and $1 is 1 full volt. And once the students started hearing it that way, a lot of them really did catch on, because if I tell them a circuit starts with $12.60, and by the time it gets to the load, there's only $11.40 left. Well, then the question becomes, where did the $1.20 go? And that is exactly the question I want them asking. That right there is voltage drop. You're looking for where the money got spent, or maybe more accurately, where it got wasted. And once they start thinking that way, the number on the screen means something. It is not just a number anymore. It is loss. It is missing pressure. It is available energy that did not make it to the load. Now let me give you a real example, because I think that is where this thing starts to really settle in. This was an early 2000 Chevrolet truck, 5.3 liter slow crank complaint. Pretty normal kind of deal, and the backstory on it was exactly the kind of thing we see all the time. Somebody had already put a starter on it, and guess what? It's still cranked slow. Well, now you got a problem, because the big obvious part got changed, and the symptom stayed, and that ought to tell a technician something right there. If you put a major component on it, and the symptom basically does not change, you better stop thinking parts and start thinking circuit. So I went into that one with a meter. We will just call it the Snap-on 525. And I checked the circuit under crank. Not static, not key, on engine off, under actual crank load, and the ground side was not terrible. I was seeing about 3/10 of a volt. So in the money method, that is 30 cents. Not ideal. Maybe a little more than I would love to see, but not enough by itself to explain a severe slow crank. Then I checked the positive side, and that is where the whole story changed. That thing was climbing to almost 2.5 volts on extended crank. Now that is big. That is $2.50 gone. Just trying to get from the battery to the starter. So stop and think about that for a minute. If you started with $12.60 and you lose $2.50 on the positive side and another 30 cents on the negative side. Now the starter is trying to operate with about $9.80. Well, of course it cranks slow. Of course it does. And the other thing that really stood out, the cable was getting warm. Not blazing hot instantly, but it was getting warm enough that you knew something was wrong. And that is a real clue, because anytime you're heating the cable up, you are spending energy in the cable instead of in the starter. The cable had basically become a resistor. And what had happened was somebody had put on one of these cheap, undersized cables. Looked okay at first glance, fit the application kind of visually, bolted on, probably seemed fine to whoever put it on. But electrically, it was absolutely the wrong part for the job. And if they would have cranked that truck long enough, I really believe that cables would have failed. It was acting more like a lightweight jumper cable than a proper starter feed. So what did the voltage drop test do there? It told the truth. It did not care that the starter was new. It did not care what somebody already did. It did not care what looked clean. It simply told the truth about the circuit under load. And that is why I keep saying it. Voltage drop is a truth test. Now let's move away from high current for a second, because a lot of people hear voltage drop and they think big cables, starter motors, maybe alternator output circuits, and yes, that is part of it. But that is not the whole story. Think about a power seat. I had one where the seat would move forward, okay, it's not perfect maybe, but it moved forward well enough, and then when you tried to move it backward, it was weak, real weak, just did not have any authority to it. And that can fool people, because they think, well, the motor works, it goes one direction, so why would it not go the other direction just as well? Well, because the path is different. That is the answer. There was corrosion in the switch assembly, and because of how that directional circuit worked, one direction had a reasonably decent path, and the other did not. So the motor was not the root problem. The voltage getting to the motor was the problem. And this is where students get trapped a lot of times. They focus on the thing that moves, they focus on the motor, the actuator, the bulb, the load, because that is the thing they can see. But the real problem is often upstream, or sometimes on the return side, in what is feeding it. So in the money method, maybe one direction costs you 10 cents. Fine, no big deal. That is 100 millivolts, but the opposite direction maybe costs you $1.40, 1.4 volts, because the switch contacts are corroded and dropping the voltage. Well, then the motor is starving. That is not a bad motor diagnosis. That is a bad delivery diagnosis. And that is a big distinction. Now, another one that technicians have seen for years, and students can relate to it pretty easily, is dimming headlights under heavy load. Now, this was easier to see with the older incandescent lamps. LEDs kind of hide some of this behavior. But on the older systems, you could absolutely watch it happen. Turn on the blower, headlights, rear defogger, maybe the heater, everything you can pile onto it. And the lights would kind of dip, and a lot of people would immediately say alternator, battery, charging issue. And sometimes, yes, sure, that can be the case. But a lot of times the real problem is the chassis ground. The return path is weak. So the way I like to check that is simple. Put the black lead on the battery negative post itself, not the terminal, the post. Then put the red lead on a known good chassis or body ground. Start the vehicle. Turn on every load you can get your hands on and watch the meter. And we are not going to allow much there. Broad teaching number, 200 to 300 millivolts in a lot of cases is about all I want to see. So that is 20 to 30 cents in the money method. A healthy body ground should not be spending much money. But when the problem is real, and this is kind of interesting, it is usually not just a little bit bad, usually it is severe. You do not usually get this nice middle of the road little number where you kind of wonder about it. A lot of times when you turn everything on and the ground is bad, it just flat out shows up. 1 volt, 2 volts, multiple volts. At that point the meter is not whispering to you, it is hollering. And once that return path gets bad enough, current starts finding other ways home. Now that is where the conversation gets a lot more serious, because if the intended ground path is not doing its job, the vehicle will improvise. And that is never a good thing. I have seen evidence over the years, and this goes back a ways, where that current found its way through drivetrain components, differential bearings, U-joints, transmission parts, all trying to get back through the engine and ultimately back to the battery negative. And the damage it can do does not always look like ordinary wear. Sometimes it looks like little arc marks, little pits, little gall marks, almost like a mouse had been nibbling on the surface. It just does not look normal. So now voltage drop is not just about weak performance. Now it is about hidden damage paths. And I think that is a really important teaching point because it makes the whole topic bigger. It is not just the starter cranks slow, it is not just the seat moves weak, it is not just the lights dim, it is the idea that poor current return can damage things you were not even thinking about. And that is why I do not like teaching voltage drop as just a procedure. I like teaching it as a thought process. You're asking the circuit, where is the pressure being lost? Where is the energy being spent? And is that spending legitimate, or is it happening in a place where it absolutely should not be happening? That is the question. And once a student kind of grabs onto that, the meter changes in their mind. It is not just a handheld box anymore. It becomes an analyzer. It becomes a truth tool. It becomes a way to make the invisible visible. And that is really what automotive electrical diagnosis is all about. Now, one other point I do not want to leave out, because people sometimes put voltage drop only in the high current box, but that is not right either. Think about a 5-volt reference circuit on a sensor. Now maybe that circuit has $5 available, 5.00 volts, and maybe a poor ground or bad signal return is costing you 20 cents. Well, that is 200 millivolts. On a high current starter cable, 200 millivolts may not scare you all that much. On a precision sensor circuit, 200 millivolts can matter a whole lot. That can skew a signal. That can change the data. that can send you down the wrong road. So context matters. The number has to be judged in the kind of circuit you're working on. And I think that is another place where students grow when they stop looking for one magic number that fits everything and they start asking, what kind of circuit is this? What should it be doing? How much loss is reasonable here? That is a more mature way to diagnose. So if I was wrapping this whole thing up and kind of bringing it back around, I would say it this way. Voltage drop testing is still one of the best tools we have. It cuts through guessing. It cuts through parts swapping. It cuts through what looks clean and what looks ugly and what somebody already replaced. It tells you what the circuit is actually doing under load in the real world. Whether that is a starter circuit with the wrong cable, a power seat with switch corrosion, a weak body ground causing lights to dim, or a sensor circuit with a distorted low voltage signal, the principle stays the same. Start with what should be available, measure what is actually arriving, then account for what got lost on the way there. Find where the money went, and most of the time, you're going to find the fault. And in my opinion, that is still one of the most practical lessons we can teach in automotive electrical diagnosis. Well, that's it for now. Have a great day.